Hello there. Don't you love it when everything doesn't go great? Welcome to part 3 of the Q&A streams. Jerry Buxton here, and I'm just streaming for the purpose of question and answer. Answering any questions that you have about AMSAT Engineering. I'll talk a little bit about stuff from various presentations that I have. I'm working at a slight disadvantage because my main PC, she blew her water pump there Sunday night, conveniently right after I had the article run in ANS, so I'm working off my laptop, and that makes it a little bit of a trick because I'm used to having more screens, and things are kind of programmed, to help it go along. So I'm going to check the chat here and see if, there we go, there's anybody out there. If anybody's out there, say hi. You don't have to ask a question or whatever. I just want to make sure all the streams are running. Twitch is hard for me to find the chat, but it should carry over. They all come together in what's called Beam. Beam is a streaming service that actually then will let you multi-stream to other streaming services. And in my case, I'm using it for YouTube and Twitch because those are the only other two streaming services that I ever had. And given that, I thought today, any questions, doesn't even have to be a question, just a topic, and I'll talk about the topic. That works as well. The idea is when I do presentations, such as the one that I have on the screen, which is the one that I had put together for Hamvention this year, I usually get 20 minutes, or maybe at Symposium, 40 minutes to talk about stuff. And if you saw the presentation from Hamvention this year, you can put a lot into 20 minutes, but you can't go very deep with any of it. So the idea for having Q&A is to be able to delve into some things, further, so that everybody has more understanding of what's going on, or, again, questions, or just wants to hear about what's being worked on specifically. In just a moment, I've finished my Coke here, so I was trying to sneak a snack in before showtime, if you will. Pardon me. Got to have that little Coca-Cola push, right? I grew up with this stuff. What can I say? So I thought I'd run down through some of the items, because specifically mentioning that what was done for Hamvention on the video that I made for Hamvention, it touches on a lot of things, but it was very rapid. And taking in a little further depth, I also have a couple presentations that I had from Symposium, and actually Symposium plus, what else did I put on here? Sorry, I have, Zach Metzinger did a presentation at Symposium also about microwaves, the microwaves that were radios that we're carrying into with golf and beyond. And that would include probably Fox Plus. I'll have to leave it at a probably, because I don't want to put any predisposed notions out there about that. I got my chat down below, so that's why I'm looking down. It's on the laptop screen. I've got my monitor that I use, 32? 28. Somewhere around 28 to 32. 4K monitor is really nice, great for gaming and all that. And lots of real estate. So anyways, let's see if we scroll through some of this. Golf program, that's, of course, the big program, if you will. It's been underway for 7 years now. Nearly 7. I mean, it was officially approved at the board of directors meeting in September, October. I believe it was October. No, it was November that year. November of 2017 at the Reno, Nevada Symposium. And so that was when we got approval for funding for Golf T. And then I found out later during Symposium that there was an opportunity to launch Golf 1 to possibly higher orbit, which is where we wanted to go with the whole program, greater orbit, larger footprint. That referring to, of course, the fact that the higher the satellite is, more coverage on Earth with the downlink and the uplink. So I shoehorned, if you will, the Golf 1 in actually at the end of the board of directors meeting to get that approved. So we have 2 of them that are approved, and then immediately turned around and went to write a couple of CSLI, the CubeSat Launch Initiative, proposals. And the proposals go to NASA. They review them to see if they are something that serves the NASA goals. And you call out specific goals for that. You categorize it as being educational, which is typically what we have done, or technology development. That's Golf T is going to be technology development. And, excuse me. Thought I saw the chat move, but my eyes are going. What can I say? So both of those, and they went literally about 2 weeks after symposium. So it was a great deal of work there. But they got them in there. We got them in there. All right, I did it all. I got them in there, and then they also were accepted. So February or March 2018 was when they officially accepted and said, we will look for launches for your spacecraft, no guarantees. Pay up to $300,000 for the launch, which is in the form of a grant, essentially. And if you go someplace that costs more than $300,000, which will get you to LEO with a 3U, according to their generalization, then you have to pay the extra. So I don't know then. Well, let's see. Let's go through the slides here. Yeah, the idea for golf was being discussed while we were doing Fox. And in that, what we did was we thought, okay, what's going to be the next step for Fox? Now, originally, Fox was supposed to be more elaborate than what we flew. Early on in the program, and it was before I was, actually before I even joined. In 2011, I came on as the systems engineer, and then 2014, I was elected Vice President of Engineering. So the AO51, which was the workhorse of EasySats, offering a lot of opportunities and such, was starting to fail. The batteries were failing. And so Tony Montero, who was the VPE at the time, he decided that they could make a change to the Fox, with the Fox 1 as it became to be called, Fox 1 series, in order to make them less elaborate, get them to space quicker, and have replacements for AO51 going up. And then you would go on to Fox 2, which would have these little deployable solar panels and such like that. During our discussions with, and this is just some of us engineers sitting around, basically, a lot of times it was done at the environmental testing, where there's quite a bit of time sitting around waiting, for example, for the bake out and such like that. So anyway, we're all talking over lunch and getting these ideas. Eric Skoog, Burns Fisher, Bob Davis, myself, and then also the conversation carried on with other people, even at the symposium in Reno. And we determined that the idea would be in order to go to higher orbits, we have to know various things quite well, and that would be propulsion for maneuvering, ADCS, attitude determination control, which is for steering, if you will, pointing, and you have to be very precise if you're going to maneuver in where you're going. We would need more power as we get more radios, go higher in orbit, and you have more devices that you have to power that are SDRs, especially, for example. They take a lot more power. You need higher power amplifiers for the downlink and such. So deployable solar panels was one of the first things, which was also, again, like Fox 2 was intended to be looking at the deployable solar panels. And the attitude determination control system then turned out to be kind of kicked off by the fact that we had worked with Ragnarok on a satellite joint venture for a satellite under NASA's CubeQuest challenge, which would basically take the satellite to lunar orbit. And AMSAT was going to provide the communications and ranging package for that. So a lot of work was done on that by the engineers in ASCENT. And that provided then the basis for the RF 10 gigahertz downlink. And the attitude determination control system, that's Heimdallr satellite, the CQC, was not selected to be one of the launches that NASA was going to fund. And it was like something to the effect that, if you want and you're in the top 5 or whatever, you still could buy a launch for like $1 million or something and go along. Of course, the Heimdallr project was not able to afford that. And Ragnarok, who was producing the ADCS, had come to us and said, look, can we want to talk to you about doing a CSLI so that we can fly our ADCS and get some space heritage on that. And the timing was perfect. I said, hey, let's put it in Golf 1 or Golf T. We'll put it in a golf satellite because it's one of the things we want to learn. And therefore, we started putting together this whole idea of developing the different systems and testing them, flying a multiple number of missions with the Golf 3U format, not necessarily carrying all, but experimenting to understand and learn all of these different systems. Therefore, there's a number of satellites that would go into orbit, initially progressively higher orbits was the idea, and then circles back around to the Golf 1. The Golf 1 then was intended to go initially to 1,200 kilometers. So Golf T would test out some of these really important basics. Golf 1 would go up to 1,200 kilometer orbit, up there in the neighborhood of AO7 and FO29. I thought that's a good place to go because if they, they're aging out, then we could have a replacement up there. Unfortunately, the orbital debris regulations got tighter, and that did not come to pass, and Golf 1 won't get out of LEO. So the work on those with the CSLI, though, still gets us the launches to be able to go up there and work on all these different systems. We can't just kind of leave behind a trail of satellites in higher orbits, at least at this time. So that's where the Golf program came into existence and how it got to be where it is. I pretty much probably touched on what's most of these slides. And one of the important things is microwave. Microwave is something that we really need to have for a progression of satellites, especially back up to the HEO or geosynchronous, or geo transfer orbit. Something in a highly elliptical orbit, basically. The VHF and UHF bands are very crowded, and there's not very much band that's allocated for satellites. Back in the time, it was probably just plenty, but a couple hundred kilohertz is kind of like hardly worth the effort. It seems like anymore. There's satellites just stepping on each other, and they can't license them any other way, really. Nobody's assigned a frequency, of course, but it is coordinated to the International Amateur Radio Union, IARU, to try to keep people from stepping on each other too much. The microwaves give the opportunity for one thing in that respect. Ton of bandwidth. 5 and 10 gigahertz have tens of megahertz of bandwidth available in the amateur radio satellite spectrum. The microwaves also lend themselves to smaller antennas because of the wavelength. Therefore, you can put in a small satellite. I mean, a 3U satellite is still, about 12 inches tall by 4 inches side. So you can put a higher gain antenna in the form of a horn or patch array and such like that, as compared to what you could do on 2 meters, 70 centimeters. So as you get farther away, higher in orbit, that gain and the ability to produce it in a much smaller space than VHF, UHF is just a no-brainer, really, in that sense. And again, the bandwidth. So that allows for a lot of different modulation signals, however you want to carry on the communications, from digital to, I guess you could do wide AM, or something like that. But so there's just a ton of bandwidth to be able to do that, kind of like the old 100 kilohertz transponder days, or even wider. So that's good stuff, and that will help. The 5 and 10 gigahertz grew out of the CubeQuest Challenge, the Heimdallr project again. Those boys, I say boys, I mean everybody, but I think it was mostly boys at the time. They were all studying what would be the best bands to use for an amateur radio satellite at the moon. And they came out on 5 and 10 gigahertz in a good part because of the availability of hardware for those bands. And that looks at it both as far as cost for the satellite as well as cost for a ground station. So there's a lot of stuff, 5 and 10 gigahertz available in probably primarily due to, of course, satellite programming or satellites, TV and such like that, but also the microwave work, terrestrial microwave work that's done by a number of organizations, such as NTMS that I mentioned earlier. That's North Texas Microwave Society. And so that became the choice, the 5 and 10 gigahertz. The 5 and 10 gigahertz then, I said, all right, we will do all of our future microwave satellites with 5 and 10 as well. And then I persuaded the Phase 4B to be a Bob McGuire, basically for Virginia Tech. He was going to go with 3 gigahertz, I think, 3 and 5 or something. And I persuaded him to go with the 5 and 10 so that we had this uniform baseline set of frequencies or bands that in moving to the era of the CubeSats, see, CubeSats what really governs that a lot because they're just such tiny real estate. There's no practicality to VHF and UHF far away. So all of the new satellites will all have 5 and 10 gigahertz, 5 and dime, if you're old enough to know what that means. But that means that you would upgrade your station to be 5 and 10 gigahertz, basically, instead of VHF and UHF, and all the future satellites would have that at least, not to mention 24 gigahertz, whatever other experimental stuff goes on with that, and not to rule out any HF stuff either. But the 5 and 10 gigahertz becomes basically your VHF and UHF is the way it's used currently in the satellite bands. We have the capability of doing 2.4 gigahertz uplinks as well, because that is a band that we explore, but also with QO100 up, then that just makes sense too, to be able to allow the use by the amateurs over there without them having to change anything, because the 10 gigahertz downlink is kind of the primary piece of that, and the 2.4 is microwave, and it got more bandwidth again for different uplinks and stuff. And did I say hi to Chris? I think I did, but if I didn't, I apologize. I see that you're watching there. And if you have any questions or topics you want me to touch on, just bring it up, because right now I'm waiting to see if there's questions and such, but just going through the most recent discussion of what's going on with everything. Again, go back to Golf T then here to continue with this. We got deployable solar panels, the ADCS. Now, Ragnarok was unable to finish their product. It was a new design, and they were unable to finish it for the deadline of the Golf T launch that we had at the time. Therefore, we had to go look for a commercial replacement. We also had to drop off of that launch because we were right down to the last minute of them delivering, and they were unable to do that, so we were going to be unable to fly. There's no way we could have replaced it with a commercial unit that quickly. Excuse me. Cat check. The CubeSpace, we got to CubeSpace for the ADCS because they're a company from South Africa. One of our members, one of our engineers, Hilliard Page, he was working with the University of Arizona or out of the University of Arizona and worked on CatSat and had a lot of experience in looking for and finding an ADCS for the CubeSats. He did a great exploration, deep dive into the various offerings that were out there that were within reasonable price, essentially, but ranking them on the price, the capabilities, and reliability, how long they've been around, and stuff like that. And that's how we came down to select CubeSpace, the South African company. And we also fly then some of this experimental stuff, and these came out of, like the RT-IHU here, the radiation tolerant IHU, came out of the work that was done. There was some work going on in ASCENT during the Gulf, or the Fox days, if you will, that to look for an IHU, a COTS, in other words, cheap, basically, but a commercial off-the-shelf components IHU, internal housekeeping unit, or the flight computer, that would be able to withstand, say, random events single event upsets and such like that. The IHUs that flew on the Fox satellites were designed, the whole Fox basically was designed to be kind of happily dumb and KISS, keep it simple. So the basis of it, short story, is that the IHU was not doing anything that was mission critical, really. The mission being the amateur radio satellite portion. So it wasn't doing anything mission critical. It would just keep a copy of what it was doing in magnetic RAM, MRAM, and then when they did have an upset and the thing rebooted, it would just go, hey, what was I doing? And go back to work. And that worked very well. We had a lot of upsets in the South Atlantic anomaly, and I mean a lot. It was originally discussed in the development of Fox that, well, it's going to be every time it goes through there, or it's only going to be once a day, once a week. It turned out to probably be once every few days, I guess. It just depends on how deep through it went, I guess. But so it would reset a bunch of times. The RT-IHU is supposed to be able to withstand that because there are two processors and there's two cores on each chip. So there's two chips, processors, two cores on each chip. And if I understand correctly, the cores are aligned 90 degrees to each other, therefore hopefully mitigating the fact that, you know, that both cores are going to go at once from some particle. But between the two processors, then, they're capable of doing a hot swap or doing voting, if you will, checking each other's health. And if one of them gets upset, the other one says, okay, I got it, while that one reboots. And hopefully that would allow us to have the ability to fly more mission-critical software in the IHU as something that we're going to need as we get more complicated with the satellites, excuse me, but also within the bounds of cost versus the radiation. Now, as long as we're in LEO, there's going to be some radiation, but nothing compared to what HEO will do to us. Nonetheless, we're learning as we go. And, sorry, just checking the chat again. So the microwave, another good mention of the microwave for golf is that, or golf T, is that we have the capability to work all these bands, 1.2, 2.4, 5, and 10 gigahertz. Whether or not we'll use those, probably test them, but the whole point of golf is actually delineated in the CubeSat Launch Initiative proposal. It's got to do the deployable solar panels, the ADCS, the radiation tolerant IHU, and a SDR 10 gigahertz downlink high speed data transfer, which at LEO is going to be a zipper, but we're shooting for 1 megabit for starters. And so that's the experimental portion of it. Golf T is a technology CSLI. So what we have come up with, though, is the fact that when the antenna was designed, excuse me, allergy season, what can I say? The development of the antenna for the uplink, it's a multi-band, wideband antenna that covers 1.2, 2.4, 5, 10 gigahertz. It also does the GPS L1, L2, and we added a 70 centimeter, 435 megahertz little pickup to pick off the downlink of the transponder signal. The transponder base transponder will be a VHF UHF 30 kilohertz bandwidth transponder, as in AO109. Husky Sat, the upcoming MESAT, main satellite that's supposed to launch, I believe. Yeah, Wednesday. Currently, no earlier than. That's always the catchphrase, right? So the that pick at 70 centimeters, then the SDR is means it'll pick that off and it will rebroadcast it essentially on 10 gigahertz. So what you do is you have the opportunity to be actually working VHF X-band, VX mode versus VU and other combinations such like that. And that adds something new and also a gateway or an opening for people to start learning 10 gigahertz, where it's, so basically optional and experimenter type of thing as people get into experimenting, receiving that and receiving, for example, the telemetry, the high-speed telemetry, as well as being able to work the transponder and hear themselves on the X-band downlink or work somebody else that way. The idea is, just the whole idea over the period, especially of golf, what I wanted to do was begin that draw into microwaves to help give people an easy start to it instead of just all of a sudden launching a HEO and going, hey, you're going to need this station to work that, right? That would be pretty quiet on there, I bet, if we did that at least for a while. So let's see now, back to the slide here for reference. Checking the chat there. You know what? Let me have a quick look just over to the actual website stuff and see if anybody added something on YouTube. Apparently not. And Twitch. Apparently not, although I'm not sure how to see my own chat on there. But they should be feeding back to Beam, and they did yesterday, so pardon me, I'm going to go with that. Hang on just a minute. My nose is so itchy, it's crazy here. Well, now that makes a difference. So, yeah, I'm just going to keep on talking. I don't know. I think, Chris, you're still there. I don't know if anybody else is actually on. And, people will hopefully watch this in the post, if you will, because it'll be, I believe YouTube calls it on the DVR, but the playback will be available for as long as I want it to be, I guess. The orbits. Okay, I mentioned about how we wanted golf to step its way up to go higher, and the initial launch for Golf T, 500 to 550 kilometers. We'd really like to go a little bit higher, but because of the orbital debris rules, and what used to be a 25-year after end of mission to burn up to decay rate is now 5 years after end of mission. So there is a limit to how high we can go with this 3U satellite, which is very much related to the orientation of the satellite. And I should have thought of that before I could put a drawing in there. I don't have all the drawings available on my laptop that I would be able to pull off on my main PC. So that's kind of like what cripples this a bit. I do have these presentations that I always just push over to my OneDrive when I'm going to go somewhere to do a presentation, so it's there for backup at least. And that's unfortunately then all the pictures that I have to work with. So back to the point, 500 to 550 kilometers. If we go above that, because we have the deployable solar panels, that creates a greater surface area, if you will, that if our orbit is carrying us, like if we're pointing to the sun for best power, and that's in the path of the orbit, sun-synchronous orbit, for example, then that's a lot of drag, and that's going to bring you down real quick. So we could go higher, 625, 650 kilometers even, and this is all dependent on the sunspot cycle as well because of the heating of the atmosphere and expansion. We could go higher if we were flying in that configuration in order to bring ourselves down within the time limit. On the other hand, if we wound up so that the solar panels are pointing, I don't know if you can see my hand here. Let me look. Yeah, it works. So the solar panels are sideways into the path of the orbit. Then there's going to be way less drag, and therefore it would stay up longer. So we can't go to maybe 625 because of the amount of time that you have in order to return. And then the worst case scenario is the Z end, the top of it, if you will, top or bottom, zipping along in that plane with the solar panels also basically perpendicular. That could last. Even in the projections with the 25-year rule, if we got to 650 or 675, I think it was, then if it had to fly in that orientation to get best sun, it's going to be up there a real long time. So it gets very tricky then. Above about 550 is about the best NASA is going to go in the launch that they provide us. We might be able to buy something higher, but it's all on us to ensure that we can meet the orbital debris regulations, and that's true even with the NASA launch. They are just very much better at giving you guidance on it because they're the ones paying for the launch, actually, right? So they don't want to be putting up any boo-boos and kind of ruining their opportunity to give away the free launches because they like doing that. That's what the government likes to do. NASA spends money, gives away the opportunities, the technology. It's good stuff. So that means that, okay, 500 to 550 for Golf T. That'll bring it back down, actually, if it launches when we're thinking in about a year and a half. That means it would, I think, get about a 4-year orbit lifetime. So it couldn't, even if it could go a 5-year mission, it wouldn't matter. It's going to be back in about 5 years because of the solar cycle. You launch so that most of your mission anyway is at least at the bottom of the solar cycle, then you're going to stay up there longer because the atmosphere, basically shrinks from cooling. It's not being heated up by the sun as much, so there's less drag. There's also the kind of practical hardware limit, if you will, in that when you get up in that area above 550 kilometers, 5 to 8 or so, and even some a little bit lower, is where Starlink satellites are going. And they, of course, only have a portion of the number that they want to put up there. But that creates a mob of satellites that you don't want to get into, because if we're not able to control ours yet, and we cannot dodge them, then it's going to be a mess up there, obviously. Go crashing into stuff. People are going to be so pissed off. And I get almost daily, but at least every time that SpaceX does a launch of Starlink, I will get CDM messages, which is conjunction. What the heck does it stand for? Conjunction something message. Sorry, just drawing a blank right now. Conjunction data message. That's it. And it tells you that hey, you're going to come within about roughly 100 kilometers of each other. Excuse me, 100 meters. 100 meters. And every time that's where the opposing satellite, because all of our Foxes or whoever's getting the message, we can't maneuver them, so you can hope that the other guy can. That doesn't mean they're going to hit. If they say they're going to miss by 100 meters, they're probably going to miss by 100 meters. And a lot of times that number goes up as the calculations get revised over some days where they're studying the orbit a lot better. But then Starlink, typically, all of a sudden, it goes from 100 to 800 meters or something, and then it's not even a conjunction anymore. So they are maneuvering their stuff out of the way anyway in going to their orbit, or making a little extra maneuver to stay out of our way. We were there first, right? I mentioned everything about the test and qualification of the new technologies, and I forgot to put my chat back on. So Billy Bob Joe Dirt, howdy, from Texas. How you doing? This I don't know, I can't tell by your name, but your sign on there that this is Amateur Radio Satellites, AMSAT. If you're familiar with exactly what that means, then you know why you're here. Whether or not, you can ask questions at any time about what we're doing, and I'm talking about all the engineering projects we do. AMSAT is a nonprofit corporation formed in 1969, amateur radio operators, all volunteers, nobody gets paid, and we come together when we build amateur radios that are in or are satellites, essentially. That's what we do because amateur radio has a variety of facets of experimentation and stuff that you can do with radio, and this is one that we just find to be pretty cool, so that's what we do. And I'm talking about all the current stuff that we're doing. For anybody else who has joined, and I can't tell if you've joined or not necessarily, that Golf project is the biggest current project we have to go bigger satellites, higher orbits. CubeSats are based on a format of about a 4-inch cube. So all this isn't 4-inch cube, but you get the idea. So a 1U CubeSat is about as big as one and a half of these boxes or so. Very tiny, but we can put a lot of stuff in them. The Golf are going to be 3U, so they're about 3 times that big, which really sounds like, whoa, you can put a lot more stuff in there. And you can, but it's still never enough, right? There's a lot of things that have to be miniaturized really to go in there. So that a lot of this stuff that we get back into the orbital debris where we have to not create any, the stuff that you can use to steer, like the ADCS, the ADCS that's going to fly is probably close to this size, the whole unit. So it takes up about, what's half of a third, right? A sixth or something of the satellite, and a little bit more for connectors and such to get on the bus. The propulsion type of things, those all take up a lot of space when you put them into a little cube like that. So that gets to be a challenge as well. And that's what we're working on with Golf, is to fly these missions where we learn to control the satellite in order to get higher than we can right now. With the attitude control, the propulsion in order to maneuver and not hit the Starlink or vice versa. Right, so I'm just going through slides that I have from various presentations. This is the most recent one that I put together for Hamvention. And didn't get to go. Matter of fact, I left that morning and got back in time for supper that night because all the flights were being canceled out of DFW all day long. I was on like 2 or 3 flights before I told them, forget it. By the time I get there, my spot at the show will be over anyway, so. What was I going to mention there? Oh, I just wanted to say that when I'm looking down there and staring down, that's because that's where the chat is. Golf 1 then, Golf 1's the follow-up to Golf T. Golf T is the technology exploration to find out if our ideas for more power, deployable panels, steering with the ADCS, that's also to point antennas like the 10 gigahertz microwave antenna, and the radiation-tolerant IHU. This stuff all under test with Golf T. Golf 1 then is expected to fly with the same stuff with modifications made to what we'd learn, say, perhaps in the final build, the flight model build, and the earlier parts of flight for Golf T. We will, of course, improve that or correct whatever we can to go into Golf 1. Golf 1 puts us back into the business of being what is a more typical AMSAT mission, not so much full technology exploration, but to actually be an educational-based satellite. Amateur radio education, that's educational in itself because you have the just the whole idea of the radio. But how's the amateur radio built? What does it do? What kind of operations can you do with it? One thing that I think often gets overlooked here in the U.S., pardon me, and maybe Western Hemisphere, if you will, is that these satellites are all worldwide because they're orbiting the Earth. They're not in the same spot all the time like a geostationary satellite. So there's hams all around the world that can use them. And there are a lot of countries where they can't just go to the store and buy like we do, or it costs them an arm and a leg to do it and get it imported or something like that. And therefore, it's, to me, and in a rough opinion, they're doing a lot more experimenting and with the amateur radio science, if you will, because they're actually putting together radios out of kit-built stuff from what you see and learn and what the satellite opportunities offer you. So there is a good point to the simplicity of the satellites, VHF, UHF, for example. That's why we will carry that forth until I guess you'd say critical mass for microwave or something, in either the fact that there are a number of hams that are ready to use that, or we get to the distances where that's the only thing that's practical. You could probably keep VHF, UHF and use it for FT8, FT4 or something. There are proponents of that. We'll see. We build what the users want, but to an extent we also have to push it because the engineers are the ones doing the building, volunteering their time. If they want to build a microwave radio, then come on down and we'll do it and we'll fly it. Doesn't mean it's going to be on every flight and what have you. So there you go. We have a lot of opportunity with the educational. So the educational is not only amateur radio, the educational is also STEM, science, technology, engineering, and math based education. And students will build experiments. Fox 1 was extremely popular with that because we had 4 slots on that little satellite, 4 circuit board slots that universities typically, partners, they would build experiments. We had experiments from Virginia Tech, Vanderbilt, ISD, and University of Iowa on the Fox satellites. These, and one of our own, actually, with the L-band uplink. So that provides the kids, everybody's a kid if you have fun doing this, the opportunity to get the education in whatever satellite experiment article they want to learn or fly without having to build the whole satellite. And we will host that for them, fly it. And so that's a great outreach there too. All the science, because it's amateur radio, everything except our command and control cannot be encrypted because it's amateur radio. Amateur radio is totally open. You cannot have any encryption at all except for our command and control, just because that, obviously you don't want somebody stealing your satellite, if you will. So the science that comes down from the telemetry, from whatever experiments are going on, is all can be received by any amateur or anyone with a VHF, UHF receiver, actually. And we provide free software called Fox Telem from the Fox satellites, telemetry, that your radio can feed that telemetry signal to. It decodes it all. It displays it real pretty. And therefore you can watch and you can see satellite health and such, but you can also see the results of the experiments that are being carried. In addition, the Fox Telem software, it's elective but defaulted to on, I believe. It's going to send all of the data you get to our server, our central scrutinizer, I call it. But the AMSAT servers aggregates all of that, so that all of that science is also available online for download for the students who created the experiment, that because it's being gathered all around the world by hams, because the telemetry is always running. It's not just running over a particular ground station at the school. And so, but that means that anybody who's receiving that, decoding it, can also learn from it. You can use it in the classroom, you can use it in your living room, whatever. And so that's another great part of the educational outreach, I think. Not just the students building the experiments here in the U.S. so far has been the experience, they're all here in the U.S., but also students everywhere being able to participate in that. I think that's like cool beans, And Five and Dime will come into full swing with Golf Tee. Not that it will be five and dime only. It's still going to be VHF, UHF as well. It'll probably be all handled by an SDR, depending on how our development comes along. Right now, we are flying an ETIS E310 SDR on Golf T. Plan is that that would go to Golf 1. The ETIS E310 could not be relayed out on a different circuit board to get it down to a size of a circuit board that typically goes in the satellite stack, which is about 4 by 4 inches, a little bit less. So because we couldn't do that, we had to really do a monkey business layout for. Hang on, got a slide on that stuff over here. For the stack being the avionics stack inside of the, play this and make it big. Whoa, look at that. So this is the E310 on the lower right. I forgot what we were describing with this piece of the circuit board that's in there. This might be this is the SSPA, so the 10 gigahertz solid state power amplifier for the downlink there. It's 1 watt. And over on the left, big circle, this is what one of the incarnations of the satellite bus, the avionics bus, which normally would be a stack, what we would like to have, like that left-hand stack where the letters are all in the right orientation for you. That is like what flew on the Fox 1. It's got 8 millimeters of separation between each board, basically by design in order to fit that many boards into a 1U CubeSat, also because it's the size of the connectors. And so we carry that with what's over here, because the stuff that's on this stack over here is actually from the Fox 1 designs. At the bottom of that, you see the ETIS E310 layout there. Even the raw circuit boards outside the box, they're too big to fit in either that vertical or horizontal orientation that the others are in. Therefore, we had to design around it, and that's why half of the stack is what we call transverse, or otherwise not in the same orientation vertically as we would like to see it. So if we can get the E310 or that type of a SDR redesigned, relayed out to be on that 4 by 4 inch PCB, or a couple of them, then that makes it a lot nicer for the Golf T or the Golf 1 satellite, and any of our hosted experiments. It gives obviously gives a lot more room. Excuse me. And let me see, mic's still good. So that's, hopefully we'll be able to fly the new SDR-B, it's called, just because it's version B, if you will. That's being worked on in ASCENT, and if it's ready, I'll put it on Golf 1. If it's not, then we'll still stick with the E310 for now. We realize that we're going to want to have our own SDR design, well, just because we would want our own SDR design anyway, but also for the future satellites, the higher orbit and stuff like that. More versatile to be able to do VHF, UHF, 2.4, 5, 10 gigahertz, and without any conversion in there, possibly. I'm not sure if that's entirely true, but still, that we would have a solid state radio on the satellite rather than combination solid state. And again, on this left stack here in the middle, you see ICR and RXTX. That is the transponder, linear transponder module we call it, but the transponder from AL109, Husky Sat 1, and now MESat 1, MainSat. So with Golf 1, we're running along with having basically full-blown SDR. We would not carry that VHF, UHF legacy equipment. If there's any chance that we may have a rocky start with the SDR, then I will fly that, because that's the fallback for everything. On Golf T, that legacy IHU and transponder, that is there. Because, well, for one thing, we know it works. Therefore, when the satellite starts up, we know how to communicate with our equipment there through that improved command receiver and such. But also, if everything else fails, basically, then this legacy transponder will still operate. And that would be true in the sense of what flies on the SDR. And that's something that actually came forward from the Golf. And I forgot about that when I was talking about the design, not Golf, Fox. The Fox 1 being simple, KISS principle and stuff, and the IHU not being mission critical. And they were FM repeaters, although the transponder was introduced with the AL109. But they don't need the IHU to operate. They don't need any computer to operate them. They'll be just like a regular repeater if there's power. But if the internal housekeeping unit, the IHU, quits working, controlling it for the different modes it might be in, it's just going to go FM repeater. And they did that. At least a couple of them would be in FM repeater mode when the IHU did not have enough juice to boot up, basically. They were on very low voltage, but it was just enough to squeak out of the repeater. So that's the fallback, and the same thing with flying that in Golf T and then possibly Golf 1. Because if all else fails, I want to have an amateur radio satellite. That's what we do, right? And let's see on the microwave a little bit more again. The 2.4 gigahertz uplink to relate with the hams over there using QO100. L-band 1.2 gigahertz. That's not a worldwide type of thing. I think it's only region 2 and maybe only region 2. I forget. But we might use that. That might be a good command uplink, or at least fallback command uplink or something like that. But I don't see it being a worldwide available thing. So 2.4 and 5 uplink, 10 gigahertz downlink, yes, plus VHF, UHF. But that's not the microwave part. This talks about Golf T and its readiness. When will it be ready to deliver? We've been working on it for almost 7 years now. I don't know how well you can see the timeline there, to tell you the truth. Blow it up a little bit, maybe. Well, that little thing that just flew by says handover readiness date. And that is when the satellite is ready to be put on a rocket. That's what we're, that's the date that we aim for to give to NASA. And they're watching everything as we go along, of course. You go back to, and I hope I did this. Nope. Back it up then. Okay, so Golf T, we're talking December 1st, 2025. That's completion of the satellite. We're at just prior to PDR, the preliminary design review right now, expected to be August, I believe. And following the PDR, we will start building a satellite with all of the systems that were processed through PDR. And this is about the 4th PDR we're going to be having. And comes March of next year, March 26th, it's the second from the bottom line there. That's the CDR date. That is the critical design review. PDR, preliminary design review, if I didn't say that. CDR is critical design review. That's where we've built a satellite, either both in the flat form, all hooked together, if you will, on a table, and with all the different systems operating in conjunction with each other and as they should, solely or together. And then also in a stack, put into a satellite, an actual satellite. Will it fit into that? Probably to an extent, some of the solar panels on it, but not entirely packed with solar panels like it would be to fly. That's the engineering model, essentially. So the engineering model is what we've put together after PDR. We test the heck out of it and determine for CDR, is this stuff good to fly? Critical design review. If not, we're going to have to make some revisions. If so, then we go ahead and start building a flight model, a flight spare. And then that's what carries us down to essentially that December 1st of 2025. So it's about 9 months or so after CDR, 8, I think. That's what carries us down to that point where we say, okay, this thing has been built, it's been tested, it's been put through environmental testing, which is shock testing, vibration testing, and a bake-out, thermal vacuum bake-out, which gets rid of excess stuff in it that will disintegrate, will leak out of it in space, so to speak. And you want to get rid of that before you go to space because it tends to like to condense on things like camera lenses. Okay, so December 1st, 2025, basically we're saying to NASA, we're ready to put it on a rocket on that date. And then at or soon after that date, they will have found a launch for us that we accept, and we'll go to that phase of, it's about a year long typically, but it can start before we reach that completion date. So after we get past CDR and we're building the flight model, then we can actually be manifested onto a mission and start working all of the mission deliverables, the documentation, certifications, and blah, blah, as we proceed toward that date that it's ready to actually go on the rocket. And that's what puts the possibility of launching then in the first quarter of 2026, basically. I just say first quarter because, I think it would definitely be first quarter. It could be much sooner if we're manifest on that rocket before we get to the readiness date. Pardon me again. And then when Golf 1 is a year behind, December 7th, 2026. Because of the timeline of finishing, well, it can overlap the end of Golf T a little bit there, but to give ample opportunity to find out what we find out going through CDR, especially with Golf 1 or Golf T, and then hopefully a little bit of flight time if it does launch first quarter of 26 before we go into CDR and the production of the flight model for Golf 1. Okay, we see Golf T on orbit. What can we learn from that? Back out of this so I can see the chat again because I don't know if there's anything new going on there. No questions. No. Well, I'm gonna talk then. I've been talking for an hour already. Yeah, this is a push job, isn't it? Sit here and talk. So, if anybody watching is a fan of video games, specifically, this is these screenshots are all screenshots from Elite Dangerous. Elite Dangerous, I play that a lot in VR, and I'll tell you what, tooling around out in space and stuff in virtual reality is pretty keen stuff, very keen stuff. So the screenshots that I take when I'm in there are impressive. They don't look quite as impressive on 2D on a slide or just an image, but even here they look pretty decent. It's like a different background than blue, red, prisms, whatever. But I got to tell you, if you're into gaming at all and you got VR, you might want to consider taking a spin in Elite Dangerous because there's nothing like inverting yourself in space to go somewhere that just spins the whole room around you. That's pretty dang cool. Anyways, okay. Higher than Leo, specialized systems, Golf 2 and beyond. This is where we've got, and I talked about this just because I'm just rambling about all these different things. To fill in is that we have to, one thing I didn't mention was deorbit devices. This has been a catch-22 to the orbital debris, even back when it was a 25-year rule. And that is that we actually, for Golf 1 to go to the 1,200 kilometer orbit, we were given the opportunity to go to a 1,200 kilometer circular. And this was a 25-year, rule to get back. And so when I told NASA, yeah, we'll be very interested in that orbit, I said, well, how are you going to get back? Because that's the catch. You can't stay there after your satellite dies, which it would for, how long's AO7 been up there, like a bunch of years, right? I think it's 100 or so up there. I figure everybody's going to be dead in 100 years anyway, so who cares if we broke the rule? But since AMSAT's been around 55 years, there might still be somebody who wants to kick the company's butt or something. So that became okay, what are you going to do? Well, we went to work on that. I said, give me a week. And we came up with two ideas. One would be to push up to 2,000 kilometers, which is where it's a disposal area. That's where they put rocket bodies and stuff sometimes. So that stuff's up there for eternity. Not quite, really, but and it's outside the orbital debris zone where they're most concerned about it, 2,000 and below. So if you get up at 2001, interesting number, then you're up there, and you don't have to say, have to worry about reentry. Well, that was nixed because they don't want anything bumping into the rocket bodies up there. I guess they can dispose of them more handily than if we were to throw ourselves up there. They can put them in better spaced orbits or something. So coming down, 24, if I recall correctly, 24 foot per second delta V change. We slow ourselves down, and the orbit would fairly quickly spiral down to below 900 kilometers and keep going. At 900 kilometers, or 800, I think, according to their specs, there's a company that was called, I think they still are, called Tethers Unlimited. And what it is they just reel out actually kind of like probably a carpenter's tape. And that creates drag. So you reel out 30 meters of, it's 30 meters or 30 feet. Either way, you reel that out, and that creates a lot of drag. I believe some of it has to do with magnetic or electric, but in the atmosphere. And then that thing would bring you down pretty handily within a year after deploying that, I think. So these were all great ideas, NASA said, of the second one, but there are no devices that have been accepted and proven for a CubeSat to be able to do that. And in order to consider that you're going to be able to fulfill your end of the deal, you have to have a 90% reliability track record or devices in order to be considered, okay, yeah, you've done that 9 out of 9 times so far. We'll figure that you're going to be good for the 10th and beyond. So that ended that right there. Now we're in an era where just at this last CubeSat Developers Workshop in April, there are commercial providers that are coming out with these tapes, for example, or other devices for orbital debris mitigation that are being approved for CubeSat. So now there's stuff that you can buy to do that. Too late for the Golf missions that we have right now, Golf T and Golf 1, but it will mature, and then that gives some hope to that ability to be able to use and prove deorbit devices. To prove our own, which is something I considered, I thought, okay, let's take that Tethers Unlimited and we'll fly that. I said, so I was going to just stick that thing on Golf T and say, we'll fire that off after whatever period of time. And see if it augers in like it's supposed to. And if we do that, does that then give us some credibility with it'll work for Golf 1 as well? And they said, no, you got to do it like 9 times. And we don't have the money or the inclination to launch 10 satellites to burn 9 of them up and go say, hey, we're good. We can keep the 10th one up there for a little bit longer, right? So much for that. But I'm happy to see that there's going to be stuff that you can purchase that will have been rubber stamped or approved, that we can be used on a satellite in order to satisfy that